Okay, some of you were talking about AI when I came in here. So here's how to defeat your AI enemies. So I post all my stuff online, right? This is my Markov chain lecture. So I delivered this lecture in 90 minutes to a non-technical audience.
Wow.
And I started with literally nothing. And at the end, I was doing text generation.
Wow.
So that's how advanced LLMs are, okay? So and you all can be faster than this, right? Because you don't have to do a bunch of witty anecdotes because you're worried about your course evals, right? So probably you can get this down to like 40 minutes or something. Right? I don't even explain what a Markov chain is. I do an aside on dice, right? Like so, and like you don't have to. And okay, so when I made this, I didn't like look up Markov chains or something, right? I just started writing code and got it to generate text. It took me like probably an hour to make these slides and 90 minutes to present them. So like if you ever want to win an argument about AI with someone, just be like, I bet I can write a Markov chain text generator in like 45 minutes and just do it. You might want to review this first to make sure you don't get stuck anywhere, unless you already know what Markov chains are, but like this stuff is not hard. And the big like attention insight from the attention is all you need paper, that stuff only works if you have like terabytes and terabytes of data anyways. So like none of us are ever going to get to use that, right? And yeah, I also was trying to get AI to generate my slides for next week in my office, and I just gave up and wrote it myself. Because I could both type almost as fast as it could produce output text, and the things I was typing, it was what I wanted. So in a way, I am a large language model. And I've been trained only on the Bible, Infinite Jest, Detective Comics, and I've probably read one other thing. The Bible, but translated from Greek instead of Latin. Okay, so shout out the Bible. Okay, action items, welcome back. Weird 2-week split on paging and page tables. Yeah, did you all notice that, like, I don't know that page tables are complicated, but there's like a lot of words you have to use. Like, it just takes forever to describe them. And I think, personally, I'm super annoyed no one's come up with a better way to describe things than the terms physical and virtual address, which, like, those are different types. Like, they're not really both addresses. I'd almost appreciate it better if like the virtual addresses were like words or aliases or variable names or something. And they kind of are, because in practice every virtual address corresponds to some variable name in code somewhere. And so I don't really know how to deal with the SSRD thing. Oh, are any of you at SSRD on Wednesday?
I'm going to see my friends. For some reason, my friends were surprised that they didn't have me do an SSRD for my philosophy thesis. No one ever asked me, so I assumed not, but maybe.
Maybe everyone else is doing scholarship,
everyone else is doing
and it's a prank on you.
And it's a prank on me.
You're going to show up, and they'll be like, here's all of the philosophy capstones that we liked. And you'll be like, wait a minute. Why don't they like wetware? Okay. So anyways, the way I tried to solve that is there was no homework last week, and there's no lab this week. So I don't know. I don't know if that makes sense. There's a lot of ways to cover paging theory. You all probably are aware of my biases, that I am really a theoretician, and I kind of ended up teaching the system stuff because I needed a way to motivate all of the theory that I think you should be taught. So if I were left to my own devices, which is, so next year Jimmy's going to graduate, and then I get to start teaching whatever I want again. And when I do that, I'm just only going to teach radix trees. I'm going to be like, this is logically equivalent to a page table. You can figure out all the implementation details yourself. But I can't do that while there's someone here who's actually tried to write an operating system before, because those people always point out, oh, there might be some complexities here. So we're dealing with the complexities today. And in exchange for that, you're going to know a little bit less about the theory of a radix tree. Can I get a show of hands? Have any of you ever implemented a radix tree for any reason? I think it was a possible solution to an assignment last term, and I think no one used that solution. I've used 2 of them. I suspect, from like the code bases I've seen and the ways things are solved, I think humans don't use radix trees as often as they should, and I also think sometimes high-level software design decisions are made that you would not make if you were expecting to be able to use a radix tree. So I feel like the radix tree technology is underutilized, but I don't even know how you'd measure that. Anyways, so we're not doing any of that. Okay. Oh, I would like to prime your thinking. It is getting more and more relevant with each passing moment to think about how you solved the malloc assignment at the beginning of the term. It remains the case. I feel pretty good about giving you all that assignment. I have often tried to call back to the same vocabulary and try and describe things the same way. And so sort of some of the core things to think about is like, oh, you have memory, but you have to store information about memory in the memory that you're storing. So there's this sort of like recursive self-description thing going on. That's something we're just going to basically have to deal with. Okay. Last week, I talked a little bit about two different methodologies for memory allocation and management. And there were the competing formulations, segmentation and paging. And basically the difference between that is paging is fixed size and segmentation is arbitrary size. It looks to us, and I think this is an open question, it looks to us like you get better memory utilization, so you use a higher percentage of your available memory if you organize it using paging instead of segmentation. Obviously, there has to be a lot of assumptions baked into that, such as what your page size is, and then also the overhead you incur from segmentation. I do not think it is completely unreasonable to say that having to track both a size and a location is more work than tracking just a location, and you can also think of that in terms of the malloc assignment. We also introduced the multi-level page table. The way I think of this, x86-64 has 48-bit addresses. Why does it have 48-bit addresses? 32 is too few. It can address up to 64. That's a ridiculous amount of memory. So we simply don't utilize those top 64 minus 48 bits, which is 16. We tend to have page tables that are nested 4 deep. So we have do I want to say 4? 1 indexed 4, right? So we have 4 page tables. Each one of them are responsible for 12 bits worth of radix, right? So whatever 2 to the 12th is, which is 4096. So there's up to 4096 entries in each page table at each level. You never have to redirect through more than 4 page tables. And so all of these sizes happen to work out to have relatively little overhead and you to be able to use all of the information you want. We found out that our brains had been playing tricks on us, and secretly the bootloader had snuck around before our operating system woke up and set up a page table for us. This was very disappointing because we wanted to write our own page table. And it was also not very disappointing because we didn't really want to write our own page table. We sort of wanted credit for writing the page table and not to do it ourselves. So what we're going to do this week is we're going to alter the existing page table. And we are going to specifically alter it in a way that we could not possibly do unless we understood the page table. So you will know how page tables work without having to go through setting up the entire stack and heap and page tables and all of that, which is not necessarily the type of fun that I enjoy having. So what we're doing this week is we are not building page tables from scratch. We are altering existing page tables. We are going to do this using a crate. Why are we doing this? I've been growing. Okay, I'm going to say one thing. It's possible that using crates isn't bad.
Whoa.
It's possible. And the thing that makes it possible is that we would be doing a lot of bit packing otherwise, basically. And bit packing's fun like the first time you do it and then never fun again. And specifically the thing that's not fun about bit packing is looking up documentation. So what am I going to claim? I'm going to claim that using a Rust crate is a more reasonable way to figure out what arbitrary bits you have to set than reading the x86-64 documentation, which in a previous lecture I showed that a link from the blog was a dead link into a page that no longer existed. It is impossible, to my knowledge, it is impossible to maintain up to date on what the current x86-64 documentation is. The closest thing to the actual living standard for the x86-64 documentation is operating system code. And so since we would be looking at code as ground truth anyways, we might as well use the crates as the ground truth code, especially if they still work. So I am regarding the use of crates as the textbook for this class. Okay. We're going to access page tables. Yeah, that's what we're going to do. This is what a page table looks like. So what is going on here? On the left, this is left, right? Is over here left?
Yeah.
Okay, that's left. Okay, and then over here is right. This image is color inverted. Maybe that weirds you out. I don't know. It's up to you. I can't look at things that have bright colors in them. It gives me a headache. So we'll just close that. Okay, what's going on here? We have some physical memory. It is no longer reasonable in 2026 to think of memory as linear, but that hasn't stopped us so far, so we're just going to keep doing it. Pretend this is a tape from 1959, okay? So we have linearly increasing numerical memory addresses. And what do we have in them? At something very close to arbitrary locations in our linearly increasing memory addresses, we have data structures. And this data structure is the variously leveled page tables. We have a series of arrows on here. And to what do these arrows refer? These arrows are pointers, and they are pointers to physical memory addresses. So when we look in a level 4 page table, that level 4 page table lives at some memory location. What is that? That is the 4 kilobyte offset, 4 kilobyte memory location. So this is one page. Now, I said 4 kilobyte. That is size 4096 bytes. But bits. Bits? I think those are bits. No, bytes. Bytes. Yes, sorry. I was confusing bits, bytes, and words. It's bytes. 4096 is 12 bits of precision. I claimed each one of these page tables represents 12 bits of precision. So what does that mean? The minimum addressable size in the physical memory stack is increments of 4096. So that's why each of these is incremented by 4096. So we have something of size 4096. It is a page table that has 4096 entries in it. It all sort of works together there. Okay, so we have at some physical location a level 4 page table. That level 4 page table contains a table of pointers. That table of pointers includes one pointer for index 1 memory. So this is corresponding now to a virtual memory address. If I look up some virtual memory address, I get told that I will find more about that virtual memory address at this physical pointer. I follow the physical pointer to location 16 in the memory, which is right here. That is another page table of size 4096. And it contains a series of sequential dereferences, which take us to 24, where we see our level 2 page table at a 0 index. Then we have our level 2 page table, which has a 511 index. And what is this? This 1, this 0, this 511, and then the 127. Those are all 12 bits of precision of your virtual memory address. So you take the outermost 12, the next outermost 12, the next outermost 12, and the next outermost 12. And eventually that directs you to some location in physical memory. And this physical location in memory is one page. So it is size 4096. It has a physical location, but you do not look it up by its physical location. What you do is you find out where its physical location is by decomposing the virtual location, and then the MMU can give you this information here. And we can also have more than one page per page table, of course. We can have thousands of pages per page table, and all of them live in the same physical memory that the page table lives in. This graphic is theoretically correct in showing an intermingling between, well, we'll call this, perhaps this orange here is like, this is like user level memory. This is a page that someone is using, perhaps, and executing it. And they are mixed in with the page tables. The page tables are OS memory, so user level do not have access to them. They're not really supposed to know about the actual physical memory. To me, this seems extremely unreasonable. I am sure every OS in the universe crams all the page tables at a very low memory region and then places all of the user visible virtual memory somewhere else very, very far away. That was probably more important when we were dealing with actual physical memories where close geographic, spatial location mattered for things like security. Now that you're mixing these in, it's all random access. It doesn't really matter where it is numerically. Okay. I have decided that my purpose in life is to explain the merits of key value storage. Keys are virtual memory locations. They are decomposed into 4 levels. So this is great because this is both key value storage and recursion, right? Like we don't get this every day, right? We decompose the keys into levels, which are radixes of size 12. I wonder if you say radixes or radices. Has anyone ever heard another human that might know how to say this say the plural of radix? I'm not even sure it's radix. It could be radix.
I feel like radices makes more sense.
Pronounce the plural of radix.
Radices.
Rhymes with the lady sees.
Yeah, radices, ladyces.
Sure.
I like ladyces. That's cool. That's like, what if the C was a girl, right? Okay. Generate a poem about if the C was a girl.
That's never been done before.
Wow, it's going for it.
Well, do people know that it's a search engine?
So I'm going to stop. I'm stopping. Okay. I can stop anytime I want. What if the C had gender? Okay. So levels are lady C's. Okay, no, I have to say the R. Radices. Radices of virtual memory, and the values are the physical addresses. For some reason, these are all numbers, but they're not like real numbers. Minimally virtual memory, but usually also physical memory. 2 is not closer to 1 than it is to infinity. So they're not really numbers. They're symbols. And we are expressing each unique symbol using a numerical base because we have to encode them in memory somehow. But it's not like 2 is closer to 3 than it is to 7. Right? They're all the same distance from each other. So they're not located on a number line. They're discrete. So they're not numbers. The values are physical addresses. In nodes that are not leaves, the physical addresses are locations of other page tables. In nodes that are leaves, they're the locations of memory pages. Okay. Currently, at press time, what's my OS doing these days? It has an error in it? That's kind of sad. I don't really know what my OS is up to these days, but it doesn't seem to know how memory works. So someone will probably have to deal with that later. The manner in which it doesn't know how memory works, you see how I'm trying to like translate memory here? Trying to take a virtual memory address and then I'm trying to look it up. All of the memory locations we have seen thus far in our kernel are virtual. Page tables don't have a virtual address. They live in physical memory, right? So we don't have a way, we don't have the descriptive power to describe the location of a page table. So we're going to have to do something to describe the physical location of a page table. I have a limit that I'm using on this slide because I don't know another great way to express this. There's this ongoing discussion in computer science, do we have to actually make you all learn calculus or not, right? Well, here's a limit. As the size of your physical memory increases, the probability of your physical address and your virtual address being the same value converges to 0. It never goes all the way to 0. It could just happen coincidentally to be at the same location. And I think before virtual addresses became popular, the probability of a collision was so high anyway, there was no reason to use virtual addresses. Now, memory spaces are very large, both physical and virtual. I mean, 48 bits is a lot of precision, right? That's a very large number. 2 to the 40, I'm not going to figure out what 2 to the 48 is. I'd be here all day, right? It's like a 1 followed by at least 15 zeros or something. Like, it's a very large number. And so you're extremely unlikely in modern computing devices to have anything approaching a collision. So you can't just look up, if you know a page table is at location 4 kilobytes, you can't just look up that numerical address. You hit the actual page table at probability 0. And that probability actually becomes literally 0 when page tables don't even have a virtual address, right? Okay. So we have, I claim, we have no existing way to dereference a pointer to a physical address every time we have done a memory lookup. And by the way, Rust doesn't even want us looking at virtual addresses, right? They try and bundle everything up inside whatever, and they don't really want you looking at raw pointers and things of that nature. We need to go even rawer. I will think about a way to say that next year. Okay, so raw meat is dead but not cooked. So you could say alive, which is further from cooked than raw.
Depending on how recently dead, it's at least a little alive still.
At least a little alive still. Okay, so we're going to use the term sentient. So a sentient pointer.
That's going to get a lot of people on your back. Unforced error.
Yeah. Well, I am only making unforced errors today. So we have no existing way to dereference a pointer to a sentient address.
Right.
Okay. We are now going to go on a whirlwind tour of the ways to do this. Here's a fun fact. I have grown extremely convinced there's no good way to interact between physical memory and virtual memory. It seems like every single thing you do is wrong. Maybe that is a claim that you should be using the closest thing you can get to truly random. That might be true. I definitely think from my background in security, the less predictable this is, probably the better. Because as you're testing your code, you should be writing code that's not going to encounter corner cases if there's really weird memory access combinations generated. And you don't want any adversary to be able to monitor your memory addresses and learn anything about the underlying layout of memory. So I'm going to take you through a series of ways this is implemented. I suspect none of them are correct. All of them are useful, right? So there isn't a correct number of wheels to have on a car, right? But it is very useful to have 4, and sometimes useful to have 6, things of this nature. Okay, so here's one way, and this is the first way, the earliest historical way, the way that predates the bifurcation between virtual and physical memory addresses. And we just call this identity mapping. The identity relation is, folks, it's a bijection. Did you all miss bijections? I like to bring up bijections from time to time. This one's a bijection. Do I have a funny thing on that? Probably not. I don't know. Anyways, there's 2 of them. It's ejection. Okay, so we can identity map all page table addresses, but not necessarily all addresses. And we're allowed to do that because we're the OS, right? So I can just take my OS, I can take all of the physical addresses of all of the page tables, and I can just load in identities at all of the page table locations into my virtual memory address space. Now, this can go wrong in a few ways. For example, no one to my knowledge has done this, but it would be very difficult to prevent me from using floats as my virtual addresses if I wanted to, because they are still unique. And so I could float address all my page tables, and then it would be impossible to memory map them, right? That's a contrived example, but what if you have different size virtual and physical memory address? Then you're still using some sort of different type, right? You can't map 48-bit addresses into a 16-bit memory space. You can't do it, right? So this works under some conditions, but you are now making certain assumptions about your virtual and physical memory addresses, namely that they can handle the same specificity under some conditions, and that this is something that is safe to do. This slide here makes no considerations of safety, but that's okay. So this is what it looks like. It is unbelievably boring. See all those horizontal lines going directly from one number line to another line? That is the identity relation. That is a bijection. It is 1, 1. It is onto. It is, there's no way inversible is a word.
Invertible?
Thank you. Kind of like convertible, right? So this is like my Camaro GT with its top down. I would just like you to gaze at this and just really ruminate on how boring it is. This is fine. There's really nothing wrong with this. All you have to do is, as the operating system, you're responsible for every time you spin up a new page table for any reason, You grab whatever its physical memory location is, and then you throw it into the page table. All of that's done on x86 at least. The root node of the page table is at the physical memory address in the CR3 register. That's what the CR3 register is used for. So all you do is you index into CR3, you run down the radices of your new physical page frame location, you put an identity relation at the leaf node. That's it. I do think this caveat is reasonable. This clusters the virtual address space. When I, the OS, ask the MMU for some additional memory to throw my page table in there, I'm getting no guarantee what sort of numerical value it has. So these things could be at the most heinous numerical locations possible. They could be fragmenting my virtual memory space severely. And because I don't know the comparative size of these two things, they could fragment all of the virtual memory space severely. So now you no longer can specify at a software level any efficient arrangement of memory with a guarantee. Now, in the size of memory spaces we're looking at, your collision probability is 0. It is 1 over 2 to the 48, which is a huge number. So I don't think this caveat is real, but what could happen is most likely someone makes what should be a reasonable design decision, writing a device driver or something. It happens to deeply fragment your virtual memory space. You get performance degradation, and there's no way to get away from that performance degradation without moving away from identity mapping. So identity mapping has a very bad case, and that very bad case is bad enough to merit maybe not using identity mapping. It's also maybe reasonable to just use identity mapping and pay the performance cost. To me, this design decision feels very similar to a design decision I made earlier in the term, where I just didn't turn off floats in my OS because I didn't think having those 2 lines of code in my GitHub was worth doing. I understand there is some theoretical very high cost that can occur in corner cases. Identity mapping is the same way. So personally, I would never sell code that contains identity mapping. If I'm just trying to get something working quick and easily, like maybe this makes sense to do if you're just like designing a quick script for a microcontroller in some setting. So this identity mapping is, I think, like a shortcut that actually could come up in very specific circumstances if you're doing IoT or something like that. Okay, here's the bad thing that happens. Let's say I need a 1,000 kilobyte sized region. Pop quiz, how big is 1,000 kilobytes?
1,000 kilobytes.
How big is it in megabytes?
1?
How big is it in gigabytes?
0.1.
How many zeros?
3.
A lot.
You're not wrong, but I don't know if you're right. Yeah. So this is 1 megabyte and 1,000th of a gigabyte. How much of a terabyte is it? A millionth? Yes. Okay. How many terabytes do we have in our computer? I'm going to say approximately 1.
Of memory or storage?
Never mind. I don't want to teach anymore, actually. What's retirement age?
These days, never.
Oh, hey, look. AI's answering. 6. Okay.
That's no good.
I'm not sorry. Okay. Okay, so here's a problem that we may have incurred. I need 1 megabytes of virtual memory. Why would you need 1 megabyte? What a bizarre size of. Okay. It's like, oh hey, I need to store exactly 250,000 I-32s. No one has ever done that. And that's binary million. That's not decimal million. Okay. So anyways, what's going on here? If you here, we'll unbigotify this. Okay. So this thing here says 24 kilobytes, right? That's 24. This says 1,000 kilobytes. There's one more space here. How big are these things? They're 4. So there's no, if this is your virtual memory space or physical memory space, there are no contiguous regions of size 1 megabyte here. So, because like whatever you were doing when you were populating your page table, you left all these like weird gaps in it. There's no contiguous regions. So, you're incurring essentially the fragmentation problem. Somehow you have to go to some higher memory region. Now, and you have to do this some large number of times because probably you have more than one client using your memory service, right? So we argue this is bad. I argue this is insane. There's no way an MMU just doesn't give these to you linearly in physical memory, so you just start at, probably not 0, you start at whatever, and then you're just going to increase contiguously. But I don't know, I'm not an MMU. Maybe they do like high performance things I don't understand. Okay. Another con. So the first con is, of course, San Diego Comic Con. So I don't know what the second con would be. It'd probably be RustConf. So this restricts where page tables can be placed. What do I mean by that? Okay. I have a data structure. I probably wrote like a subtraction linked list, and it exists at some virtual memory location. Now, the OS requests the MMU provision memory for an additional page table entry. The MMU hands back a memory location to which my data structure is already mapped. That would incur a namespace collision, so I cannot use that physical memory. So whenever you're allocating physical memory, you now have to do 2 collision checks. You have to check against other physical memory locations and also against virtual memory locations. And this gets one worse. You now also potentially have to do this against virtual memory for every process, and there could be multiple processes with multiple memory spaces. So this one I'm convinced is bad. This is why I think you can't use identity mapping, because you cannot force the MMU to not return to you a new physical memory location that definitely doesn't correspond to any virtual memory locations you're using. So that's bad. Do you all understand how? I feel like you didn't all react to that like it's bad, but that's okay. Okay, so say I store my one megabyte of, I don't know what I'm storing. What is 1 megabyte in size? Is that like a sound file that's 2 seconds long or something? Like, well, hold on. Yeah, how big are megabytes?
Pretty big and awfully big.
What keys did I press to get that? Okay. We're gonna pipe that in WC. So this image is only 0.1 megabytes.
Yeah.
Isn't SVG? Yeah, okay, it's small.
I mean, modern images aren't
Yeah,
large.
like a megabyte seems big.
I would imagine an image like that would probably be able to be compressed not as SVG pretty well too, because there's only a couple colors going on there, and colors could have confused regions.
Can I I don't know how to convert an SVG to a PNG at the command line. I've never tried to do that before.
Pretty sure you could.
If I just type PNG to SVG or something, hey! I love computers. What's my password? Lucky guess. It was password. Never try to break into my computer. You will not feel satisfied. You'll just be like, that's all? Okay. PNG to wait, I need SVG to PNG. I'm sure we're fine. PNG to SVG help. Oh, okay.
Output name. And it looks like it doesn't do the other way around.
It doesn't. No! No. I guess it would probably be a completely different program to go the other direction, right? I mean, I know how to do it with Python. You all always are mean to
You
me.
can just use FFmpeg, I'm pretty sure. Just FFmpeg I file name with SVG file name with the PNG. Yeah, dash I.
Can I pipe into this? Okay, well, let's download it.
FFmpeg, oh yeah, download the SVG.
I img.svg.
Image.png. Or you don't need that output.
Really? You just say img.png?
Yeah.
Does not contain an image sequence pattern?
Pretty sure you can do that.
I think. Open img.png. That's fine. So that's what it was supposed to look like. That's hilarious that that's how it renders it. Everyone look up. Look at this screen.
What?
Never use computers. Okay? This is how they see the world. Okay, let's see how big it is.
Because SVGs are messed up.
That's smaller?
It's slightly bigger. Right? The other one was 22,000, right?
I thought it was. Oh, yeah, no, I just totally forgot how big it
It's
was.
slightly bigger.
Okay. What did we learn today? Identity mapping. And, oh, it's an interactive slide. Look at that. Okay. So don't identity map. I don't care if you identity map. There's like a lot of overhead. But I have certainly written systems code in my life where you just like request something over and over again until it gives you a number that satisfies constraints. I'm not like super proud of this, but I've written network code this way. Where sometimes you're like, oh, it'd be a lot easier if I get like a port number that is like a multiple of something. I don't know. So like some of my network code, it just like tries port numbers until something works. Obviously, you can't sell code that does that, but if you like just need to get something working for your final in this class, it's like that's a totally fine thing to do. Okay, so here's the alternative. We can use fixed offsets. Folks, have any of you heard of linear combinations? We can compute a line. This is y equals mx plus b. Do you all remember 7th, 8th, or 9th grade? I don't know how school works anymore, right? Yeah, so I remember. Here, AI is smart, right? Plot y equals x plus 2. Look at that. This computer could pass 8th grade, right? So this is a fixed off. Actually, this is a very aesthetically nice grid. Here, good job, computer. Okay.
What does it say? Come on, what does it say?
Thank you.
It sucks.
If you're looking for an actual good job.
Oh, God.
Not a good job, but a bad one, perhaps. I saw. Did you all see the Reddit logo pop up there?
Yeah.
One of those was Reddit. Okay.
How is it so... Gemini sucks. It's the most annoying of all of them.
Should I click on a Reddit link in class?
It's a bad thing.
I agree.
That's right. I'm streaming. Any chatters? I'm doing SSRD. Wait, how do I emoji react to this? Big ups. Oh yeah, so I don't know if you all know this, but Linux doesn't really support the way I do screen cap. So this is what all the recordings for this class look like, and somehow they have like 300 views each. Isn't that cool? And see, this is recursion. Look at this. What were we doing? Oh, I was teaching class. Okay. Fixed offset. You just add some like big old chonky number to any of your addresses. Personally, I would add 2 to the 48th because that will avoid collisions. Easy. Linear transform. I've suggested here you can add 1 billion Is that how you spell billion?
Yeah.
It's spelled Bill Ion?
How
Yeah.
else would you spell it?
I don't know how words work.
Like with a Y?
I don't like the 2 L's.
You think it should just be 1 L?
Billion.
Lyin.
B-I-L-I?
Billion.
Billion.
Actually, now that I say that,
That's so much worse.
That's probably how the French do like billion.
What if instead of, so you know how like people named Billiam go by Billy, right?
Yeah.
So what if we just called it the numbers?
A billion.
Yeah, what if we had a Billy and a Millie and a Trilly and a Quadrilly?
I'm pretty sure milli is already slang for a milligram of drugs.
Hell yeah.
Specified.
I assumed by milligram you're referring to a milligram of physical memory locations. Okay, it does not matter what the offset is. Probably, okay, it probably can't be negative. Like, I suspect there's not negative physical memory addresses, but has anyone checked? And on your Turing machine, there are negative physical memory addresses, right?
Lots of some different ways of doing memory. So the
Mhm.
kernel's in negative, and like user space is in positive.
Yeah, and then you're trusting sign bits, right?
Yeah.
And, okay, here's a pop quiz. Do we trust sign bits? Yes, you do, because this is a Rust class, and the default numerical type is an I-32. What an absolute garbage design decision. Okay,
It's a reasonable middle ground amount of memory. What would you rather have it be? A U8?
a U64.
That's too much. You don't need that. Most integer is probably going to assign to track like
I have a solution that will piss everyone off. There should be no default. You should have to type all of them.
you are the worst. You are so annoying.
There should be... I do think there at least should be a different type. There should be a different type for indexes and for values.
Yeah.
And you should have to
So
cast
the default
between
should be
them.
U size. Everything's an index, really, if you think about it.
No.
I don't think it is.
No.
No, yeah.
But I do think you should have first-class support for float indexes, but they should be into dictionaries, not into arrays. Okay, here's the example. Okay, fun fact. We all remember 8th grade. Look at this. All of these lines have the same slope. That's because y equals x plus 2 has a continuous derivative. I will trick them into letting me teach calculus someday. Someday I'm just going to cruise in here and be like, time to learn the epsilon delta definition of a limit, right? Anyone do epsilon delta? Yeah?
Which
Those
count
are
is
two
that?
COVID variants.
It's a way of teaching calc. It's the
But is that
correct
two
way
or
of teaching
three?
calc.
Or one? Like
You use it for all three of them. Yeah.
That's when you do real analysis and you want to prove that calculus works.
But, okay, so this is not on task. The early epsilon delta proofs had a logical error in them because the philosophers hadn't shown the validity of infinitesimals yet. So those proofs actually became correct thanks to the philosophers. So if you see a philosopher, say thank you. But you can't say thank you until they complete their SSRD presentation because they're not real philosophers. Okay. The 48-bit memory address space is 256 terabytes. Did I check that math? No. Should I have? Oh, it is correct. Yeah, because 50-bit address space would be 4 times larger than that. This size is sometimes referred to as large. How tired was I when I wrote this? 48 bits. What this means is I can add 10 terabytes to things, no problem. Most people don't have 10 terabytes. I don't know if any of you have 10 terabytes at home.
That sounds like something Trump would. Most people don't have 10 terabytes. We do. We have 10 terabytes.
Yeah.
You're right.
Yep. I am known to hang on every word Trump says, so that makes sense to me.
You're streaming. Don't
Yeah.
say that.
Here's something. Oh, okay, never mind. I'm not going to give an example of something I can't say while streaming. Okay.
No, I think that's a good idea. That sounds solid to me.
So we've done a little bit of talk about AI today, right? So there's things AI can't generate, right? But have you ever seen? Okay, let me phrase it this way. Imagine in your mind an arbitrary U.S. president. Just select one randomly, right?
Village Belmont.
Yeah. And have you ever seen, just the one you're thinking of right now, have you ever seen that U.S. president pass the Turing test?
No.
Right?
Whoa.
Yeah.
Crazy.
I was, so this is, okay, here's something not to do in your life, so I'll just plant the seed in your mind. Someday, some of you will have the misfortune of having jobs. Some of you might become computer science professors, but some of you might have a job. Never be sitting in a meeting thinking, has this person who is my boss, have I ever seen this person pass the Turing test? Never think that, okay? Because if you think that once, you're cooked, right? Okay, we need to create a new mapping whenever we create a new page table. How is that a limitation? Okay, this is Blog that said this, right? My claim is that it is hard for computers to remember linear combinations. What is the thing that computers are the best at?
I think numbers, I would say.
I would think it's probably numbers, and they are way better at additions than they are multiplications, right? And these are all additions. I'm not even multiplying anything. And if I am multiplying anything, it's just a bit shift, which is the type of multiplication they're good at, right? So this is like I'm storing 96 bits because I have offsets in 2 ways. I have 40 bits. Like, that is just way too easy. Okay. It doesn't allow accessing page tables of other address spaces. This makes sense. Okay. So say let's see, what is the time I want? I download a PDF from Al Gore's internet. Al Gore, not a U.S. president. Has anyone seen Al Gore pass the Turing test? Does anyone know what Al Gore looks like? Can anyone spell Al Gore?
ALGORE.
You missed the space. Nice try. You didn't even capitalize the second G, or the second word, G.
That's true, I didn't. I don't know how you heard that, but I didn't.
Yeah, I heard the lowercase. I'm gonna keep going. Okay. Fixed offsets allegedly have downsides. I was not convinced. To me, it makes sense to just add your memory size to everything, and then you'll never have collisions. Okay. Full map. What if I map the complete physical memory? So identity mapped page tables, complete physical memory, maps everything. This solves the bad thing with identity mapping, right, is you might have physical memory, virtual memory collisions specifically on page tables because you already have allocated that virtual memory. This seems cool. This should feel to you, in some abstract way, extremely convenient to the kernel, because now the kernel doesn't have to read through page tables to look up memory. It can just index directly in by physical memory locations. That should be a moderate performance increase, right? And the cost of that performance increase, you no longer have any memory isolation between any programs at all. So this completely defeats the purpose of having an OS. But it makes your OS really fast. So that's cool. Here we go. That's the same image? That can't be right. OS fill. What image is supposed to be there? No, OS fill is also wrong. That's definitely not what you mean, right? Okay. So, okay, we map all of it. I don't know what this image is showing. Okay. Doesn't that defeat the purpose? I claim that defeats the purpose. Okay, sorry, I need another spelling check. I think it's the eyes. Is this how you spell achieve?
I think so.
Looks like it.
Okay. We're going to say I'm losing my mind, and that's why all the words look misspelled to me. Because I misspell words all the time and don't notice, right? So I have both type 1 and type 2 errors. Okay. Okay. What does this mean? One process can no longer have its own memory space that is discrete from all other processes. Potentially bad. What does this mean? Remember on the malloc assignment, you had to use some of your fixed size of memory to keep track of whether you were using the fixed size of memory, which means you had to have self-referential memory where you had a bit that corresponded to a byte or a word or something and keep track of that. So with a complete map, you're having to store the page tables somewhere. Hold on. If it's a complete map, why do you need page tables? So think about that for a minute. But persuade yourself you want memory isolation. And I attempted to persuade you that you needed memory isolation last week, so I'm not going to belabor it that time. Okay, so word on the street is x86-64 can address enormous pages, up to size 2 megabytes. I'm calling these enormous. Now, there is a technical term for how big these are, and it's huge. The technical term is huge.
Yes.
I am specifically going out of my way to not say huge because it's so ridiculous that's a technical term. So just be advised, like, if your kernel spits something back to you and was like, my friend, that was huge, it's referring to the size of a page. Not a page table. The page tables are all the same size. Okay. Why is this awesome? You know this already. This cuts down on overhead. When you were implementing malloc, you had to make some kind of design decision about the minimal addressable unit. And it could have been bytes. It couldn't have been bits because then you run out of space, right? So it has to be smaller than what you're referring to. It could have been bytes or it could have been words. And this was a design decision, and depending on your use patterns, it's better to allocate bytes or words, okay? And so you've already made this bytes versus words decision. The identical design decision is, do I use huge or normal-sized pages? Not page tables, pages. So you already did this. You're so smart. Okay. Oh, right. Aside. Okay. So when you have huge pages, this impacts the performance of the translation look-aside buffer. Repeat after me. I know what the translation look-aside buffer is.
I know what the translation look-aside buffer is.
Oh, that's good. You all know that. Here's the slides on it if you need to know. I have this memory of being asked what a TLB is in an interview, and I don't know what job that would have been for, because I've never used a TLB. I know what they are for. Translation look-aside buffer. It's a small memory scratch space used to save recent lookups, so you don't have to go all the way through the page table. It's only a performance optimization. It doesn't do anything theoretically, right? But at high probability, if you looked up a memory address recently, it's in the translation look-aside buffer, so you don't have to index all the way through your page tables. So this is one of the big performance benefits that came in like the 90s or something. It's ancient now. But it's a good example of caching. Okay. Think, pair, share. Turn to your nearest fellow human. So you're not allowed to talk to any U.S. presidents. And describe what the TLB is as if you were asked during a job interview. You have 2 minutes to go both directions. I'm starting a 4-minute timer, and you will change at 2 minutes. Okay? I practice doing prompts. You'll have to talk to them or me. You can talk to your favorite sitting U.S. president.
I have no idea. The program and then you make the slide. I see it
Stores.
Oh,
Translation means that we don't have to go here and translation. Theoretically, it doesn't change anything.
That's probably
But
one.
there are a couple of times that it's because of memory defenses. You can't assume that the page table is
Oh, boy, that is.
in that case, the page table
Success factors is just like that always.
reset everything inside of it. And you know, like if you have a process, which is you have a process, they have page tables, so you can't use the same page table. There's also a security issue.
It is a cache in the cache previous lookups from page tables to reduce the amount.
Got really quiet in here. Are you all slacking?
we know what the thing is so well that it didn't take that long to talk about it.
Yep.
Interesting. So the prompt was talk for 2 minutes. How did you complete 2 minutes of talk in under 2 minutes?
But you
We're moving very, very quickly. Or no, that makes us go slower. Okay. Or no, it's if I accelerate it very, very quickly.
So you're able to fill time, is what I've demonstrated here, right? Okay, so let me share something. From time to time, at least like in this department, we interview people to get jobs here, right? So, I don't know, you've probably been around while new people have started, right? Did someone start this year? Zach. Probably know Zach. I think Rachel started the year before that. So we interview these people. Here's something to not do when you're in a job interview. Say you get a 30-minute interview slot, and they're like, hey, we're going to ask you 6 questions. You can do division. What is 30 divided by 6? Yeah, that means you talk for 5 minutes in response to every question, right? And you can cut it like a little bit short so you have time for your questions at the end, right? Do not answer in like single word phrases the 6 questions and then awkwardly stare at your interviewer for 25 minutes. Don't do that. Do people do this? Yes. I don't think it's like reasonable to assume people know how to get interviewed. That's why I'm telling you, okay? So set your time targets, listen to the number of questions they have. If you don't know how many questions they're going to have, just assume 5, right? And try and answer appropriately to fill the appropriate amount of time. presumably, like, the cognitive theory behind why you're doing this makes sense, right? You don't want the interview to go over because that'll create negative feelings. You don't want to end early because that'll seem weird or like you're not interested or people will perceive it in a certain way, right? So if you get 2 minutes to talk about a TLB, talk about it for between 1 minute and 40 seconds and 2 minutes. Okay, that's the full map. All right. Wait, now you're all talking. I love Freudian manipulation.
I don't know if it's Freudian in particular, but manipulation. You can all get behind that.
Epsilon systems. Suffragette. Top secret.
What are they talking about? What are you talking about?
Job applications.
Okay, that's good. That's fine. Okay. All right. So the problem with temporary mapping is everything is temporary, right? Like, I don't have some hot new startup out of Silicon Valley that's making solid-state drives that last until the heat death of the universe, which would still be temporary, right? And the problem with that is all of them, they give off a little bit of heat over time, which means as long as they're turned on, we're getting closer to the heat death of the universe, right? And there's a finite amount of heat in the universe. And I use some of it to record my lecture recordings and post them on YouTube, right? That's how I use my heat. So with sufficiently little memory, especially if you can fit in a non-radix page table, you use a temporary map. So what's a temporary map? I have no idea. I can't tell what this image looks like. Okay, so the page table controls the first 2 megabytes of addresses. So we have a sort of like reserved space here, right? And so we have a reserved virtual space that doesn't correspond to a physical space. We only reserve the first virtual space. This virtual space, or this physical space, is reachable through the CR3 by following 0 index. This is at higher radix page table. So each one of these is a 0 index. Okay, so I have a page table, or a multi-level page table of depth 4, which is the standard size. I just go through all zeros. When I get to the last 0, I get a physical pointer somewhere. Where is it? Right here in physical memory. Does not matter where it is in physical memory, but it corresponds to virtual memory address 0. So if I look up zeros all the way through, there's always some sort of temporary, I don't know, scratch space or notepad or whiteboard or something there that I can use temporarily. Okay? So then we can place indices relative to that page table somewhere. So we can index out to 32, right? I'm going back and forth. And what you can do with this is you can identity map a page table to itself. So this page table is at some location. It is temporarily identity mapped by looking up virtual address index 0, okay? This allows you to have 511, because you can't use 0. This allows you to have a small, I don't know, 511 is pretty good, a small number of sort of working pages that you can always use temporarily to store any information. So you can map the 0th entry, or you can map some arbitrary entry, and you can temporarily put page table data structures at these locations. And whatever you put in them, see how these are going back and forth? You take the 9th entry, and that's just going to be at some offset. We can map it to whatever we want. This is kind of cool. And if you do this, you can then sort of skip hierarchy levels of your page table updates because you know where the physical addresses are. So, I don't know, that's cool. I feel like this is extremely sketchy, so I would not use temporary tables. One of the reasons, so sort of anything you ever write to memory is, this stuff is potentially sensitive, right? Because this is telling the contents of your physical memory address. So you're writing physical memory addresses to quasi-user visible virtual addresses, and then it's persisting in some cache somewhere until it gets overwritten. this seems really bad, and I don't necessarily see the performance benefits being there. I don't believe temporary mapping is still in use. It might be used in like niche cases for performance optimization, right? So this seems crazy to me. Like, obviously it's possible, but it stresses me out. But I don't know, it's not too complicated. So here's just the 4 steps. You identity map a level 1 table, so the level 1 table is the last radix. You map that entry to the physical frame. Then you can access the target frame directly through the virtual page. And then when you're done, you just clear that mapping. You leave all of the bits that you were writing in the same places in memory, but you can no longer see them because they're no longer populated in the page table, so they're not there. Then a sufficiently sophisticated adversary comes along and can read all of this stuff, but we don't worry about that. This does not take up that much space. That's kind of cool, right? So you're using a very small number of virtual pages. I do like that. It uses basically no physical memory at all. It uses 1 page table. And you just put a temporary page table there that has 1 lookup in it. But you can be altering you can be altering all of the higher level page tables. And so that's the temporary map. Recursion. I love recursion. Here's an exact quote. I never thought I'd see recursion used in a recursive data structure like a radix tree. Okay. Here is a question. This was a question for the class. So I wrote this down here to remind me. Do you all have a sense of like how many for loops you've written all term? Because I think I've written either 2 or 3, and 2 of them were for printing, where I was like very clearly just like looping over some text that I was writing linearly to memory locations. So I think I've written either 2 or 3 for loops this term. That did not convince me that for loops are the way to do things, which I had sort of been coming around to after writing recursion for a while, right? And there's one other thing I need to call out. I don't have it in here anymore. Remember how this used to just say loop? Wait, why does that not have a semicolon at the end of the line? I know I don't need it, but... Hold on. It's an emergency. Okay, that's better. Okay. This used to have loops at it, right? So I was a little mean to loop when I started learning Rust, but I've written, I think, as many loops as fors this term. So I didn't think about it that much, but recursion. Okay. You can allow a page table to map itself. This seems a little crazy, and it seems a little crazy not because this doesn't make sense for a multi-level page table, but because in practice, page tables are so aggressively leveled that I sort of think of a level 2 page table as a different type than a level 3 page table, which means I should not have pointers from a level 3 page table to a level 3 page table. That's how it sort of intuitively makes sense to me. But you can, of course, allow a page table to map itself. And when you have a page table map itself, so it can, you have the physical address of the current page table listed somewhere in the lookup table of the current page table. So if you index into a certain location in a page table, you look back at that same page table. And so this is allows you to repeat radices. This is, I don't know, coincidentally, I guess I'll say incidentally, logically equivalent to reserving a block of virtual memory that corresponds to those 12 bits. And not necessarily all of the memory in that 12 bits, but at certain offsets within those 12 bits. Let's see if this makes sense with an example. Okay, so here's the example. Or like I have it up on this slide, but we're gonna walk through it with text on the side next to each other. Okay. So this is the original example of a page table that was shown at the very beginning of class, and there wasn't anything interesting about it at that time. We've just preserved the same example. We thank BlogOS for generating this, but like it doesn't really matter. Okay, so we are adding one thing to this page table, which we're adding an index 511 to the level 4 page table. And this is going to map frame 4 kilobyte. So here's the 4 kilobyte frame. I don't know how visible, these arrows are okay, right? So we can see we have 0 is open, 4 kilobytes is populated with a page table. Which page table is it populated? It's populated with the level 4 page table. The level 4 page table contains at least one mapping, and that mapping is back to the same level 4 page table. So if I look up memory address with 511 in its top 12 bits, I will look at the level 4 page table once, and then I will look at the level 4 page table again and perceive it as a level 3 page table. Because I, as the OS, are expecting to see a level 3 page table if I look up a physical memory address inside a level 4 page table. That's, like, maybe extremely cool. Like, I think that's pretty cool. And by the way, if my next 12 bits also hold the numerical value 511, then I look this up as a level 2 page table, and then a level 1 page table, right? So page tables can map back to themselves, and they can map back to themselves at arbitrary virtual locations. You can make this a little bit dumber if you want, which is actually you don't only have to map 511 back to the level 4 page table. You can also like throw a 12 in here that maps back to the same location, because none of these things have to be bijections. Right, this is all symbolic mapping. So you could actually map every single entry of this to the level 4 page table. It's just then your page table doesn't work for anything. Okay. If followed, the CPU finds the same page table again. So I look at my level 4 page table. I look up the 511. I look at the same level 4 page table, but I perceive it as a level 3 page table, which means I look at the indices and I interpret the indices as being shifted 12 bits over. So this works because this was a claim in Blog. Blog claimed this only works because only x86 has level agnostic page tables. I am skeptical of that, but I don't actually know how to figure this out easily. I have never heard of anyone implementing page tables in a way that keeps track of what their level is. It's just a tree, right? So, like, I have no idea how you would design either a CPU or an OS so page tables are different data structures if they're at different levels. Like, that doesn't make sense. Maybe I can imagine having a specific leaf node, but like, why would you have a specific leaf node? You're just going to index into an actual memory location, right? So I believe every architecture has level agnostic page tables, and some of them I think have variable precision page tables, but I don't know if that's true, and I didn't know how to check. Okay. This can shorten the number of levels that the CPU traverses. Okay. You all remember the translation look-aside buffer? Okay. I look up this page table. It's in my TLB. If I go to the next level and look this up again, I'm going to hit the same page table, which is already in the TLB. So that's fast. Okay? Following the recursive entry, change the perceived radix each time. So those 511 bits correspond first to bits 48 through 36, and then 36 through 24 or something. I don't know, like that. So you can treat tables as tables of other levels. And what does this allow you to do? Well, when you get to the last level, now what you have is you're looking at a memory address that is supposed to correspond to some working memory, because that's the thing that we've stored in our page tables, right? But it's not actually working or user level memory. What's actually there at that last level is now a page table of some level. So if I go through this once, I say this is my level 4 page table, boom, circle back. Then I say it's my level 3 page table, and I circle back, then I look up the level 3 and then level 2. I never look at a level 1 page table. What I see instead is I see the memory address of this level 1 page table, which is currently living at location, where's this thing, at 32 kilobytes, right? So this 511 lookup is at 32 kilobytes. And I can write to this memory, this page table memory, as if it is just any other data structure or any other working memory. So this sort of removes the permissioning from page tables. Because I loop through it once, it consumes one of the levels of misdirection, and then I'm able to write to the page tables directly. So this is a way to, I don't know, alter, edit, read, write, I say read and write, page tables without the CPU being aware it's writing a page table, because what it's perceiving is it has indexed all the way through the page table and has started looking at working memory. just so happens the physical memory address it's looking at corresponds to a page table. Okay, let's step through the recursion. We have a recursive step 1. So I want to point out that this step 1, we loop back to where we started. So step 0 is we perform a lookup. Here's the 4 kilobyte. We can recurse multiple times. Okay. So we look up a physical memory address. No, we look up a virtual memory address that corresponds to a physical memory address. The CR3 register contains the location of the level 4 page table, so we look that up. We index in at level 511. That recurses us back because 4 kilobytes. So we save the same location in the CR3 as at offset 511. We recurse. Now what is the next thing we're going to look up? We're going to look up a 1. So this is the next bits of our virtual memory address range. That takes us to a level 3 page table. But we have already gone through this twice, so we perceive this level 3 page table as a level 2 page table, which means we only have 2 more page tables. We look up location 0 in here, and it has us looking at the level 2 page table, but perceiving it as a level 1 page table. We look up the next location, and it gives us what the OS or the CPU perceives as a memory address, even though incidentally it is actually a page table address. And of course, it doesn't matter. The page tables are stored in memory. So now I am looking at this physical memory location and the bits therein, and I'm able to read, write, edit, alter, do whatever I want with this. But any changes I make, I am making to a level 1 page table. This means I can add new memory maps to this location. So this is a way to map additional memory. I feel like this is seeming a little bit crazy to you, but I promise it's cool. You can do this to also alter. What is the difference between these? We recurse twice up here. So what's that? We put 511 in the second 12-bit chunk again. So we recurse twice. And that allows us to alter the level 2 page table. And similarly, we can alter the level 3 page table. This would have been the lab if we didn't have SSRD. Left as an exercise for the interested student. I think there's a description how to do it here. Okay. This potentially uses a lot of virtual memory. Why is that? You're gobbling up something in the level 4 page table. The level 4 page table is allocating a lot of memory. Am I really worried about deleting half a terabyte of memory when I have a 256 terabyte virtual space? I just don't think that matters. Like, that just does not seem like high overhead to me. I mean, it's like 0.25% or so. Like, it's some like hilariously small amount of information, right? So I think that's never relevant. So this is an interesting case where like the cons are there aren't any cons, right? It only allows accessing the currently active address space easily. What does this mean? Well, so you can't look up things across different page tables, but generally speaking, you want memory isolation between processes anyways. So this is good. You would incur a large amount of overhead to look up memory in another process. That's what should happen, right? That's why we have the abstraction of processes. And we haven't talked a lot about processes in this class, right? But it makes sense. You don't want iTunes to be able to read your downloads folder from your browser or something, right? And then the third and final con is like something I'm like totally underconvinced by, which is like, oh, it relies on page tables not being implemented differently at different levels. And like, who is going to implement page tables differently for different levels? That's like an absurd way to implement a data structure. Presumably at some point in your life you've implemented a binary search tree and you didn't implement a different class for every single level of the search tree, right? Like that's a weird way to do things. So my pitch on this, and I don't know, like maybe I need to think about it more or like more completely implement it myself or like try and actually run an OS with this and like see what the problems are. It really looks like there's no downsides to this because these downsides are extremely fake. So recursion, it seemed pretty awesome to me. Okay, so pirates like booty, right? So they probably like bootloaders. No, that's bootleggers. Is bootlegging a thing?
Bootlegging is a thing. It's illegal producing alcohol.
Yeah, they used to do it back in like the 70s.
And now it's pirating Hamilton, I think.
I think that's selling a pirated coffee.
That's called, it's like bootlegging, it's like...
It's someone like records it, like
It's
when
like
they're
you're
coding
like
it.
that.
Toys
Okay.
/Tumblr.
Yes. I typed in how to pirate Hamilton,
Well, you're talking about Hamilton.
and I got our Tumblr.
Yeah.
Isn't there an official recording
There
of
is,
Hamilton? I
There
thought-
is now.
Do like
After
cats or something else.
By
What?
YouTube
pirate
user Hamilton
cats.
fan.
How to pirate cats? What year?
2019.
Of course, the best
No.
one.
I meant like the actual musical.
It's the best one.
The actual
I meant
musical.
like the real one.
I don't think you can pirate musicals because they're not virtual.
No, but like there's bootlegs of people like recording it. Like
There is also a
Bootleg recording of Cats musical. Pirated. Free. Oh, I liked free at the end.
Pirated free.
Oh, okay, fair enough. I was skeptical. I didn't know there was an R musical bootlegs. What have we learned today about Reddit? Okay. Okay. Bootloading. Each of these approaches requires write access to page tables and fine-grained control of physical memory. Do you have this? Not quite, but it's going to be pretty easy to get it. So we can't create these required mappings without an existing way to access page tables. We don't know where the page tables are, so we can't even do the recursive trick yet. We can't do anything. We are in our bamboozle era, right? There used to be, I think it went out of business. There used to be a restaurant near me named Bambooza, and they could have named it Bamboozle. Why would you name your restaurant Bambooza? Okay. We, quote, need the double quote help of the bootloader. The bootloader has deprived us the privilege of suffering, and suffering is one of the great privileges, so we're a little bit sad about the bootloader. The bootloader had to set up all the page tables before our kernel could wake up, which we know because we have things like static mutes which have to be mapped somewhere, right? So the bootloader has access to the page tables. Also, someone made sure that the VGA buffer was living at the appropriate virtual memory address, and that thing doesn't correspond to a physical memory address at all, so someone had to map that. So we're going to use cargo features. I would like to point out in blog cargo features with a hyperlink, and I removed the hyperlink because I don't want you to like cargo. Maybe that's wrong. I wonder if that was wrong with me. Okay. There are two ways to solve this problem. We are going to do a complete map because it's faster and easier and the performance doesn't matter. You, dear student, are welcome to not follow this guide and just do the recursive page table. It's like 8% harder or something. Like it's not that different. So like if you want to do it recursively, do it. Right? Like I'm proud of you. And the reason I'm proud of you is because no matter what happens, I win. You either get to use key value storage or recursion, right? Like this is the best day of my life, right? Oh no, I have to decide between key value storage and recursion. That's like winning the lottery twice, right? I played charades with my family on Sunday, and the thing I had to act out was winning the lottery. And I went like this, and they guessed it. It was amazing. I scratched. You know?
Oh, sure.
Yeah.
Okay.
That makes sense.
I had something in my hand,
That
too.
was
where-
you should have acted out recursion. Or key value.
Oh, I didn't get to pick.
Well, as representative of
Yeah.
Oh, that's
Clearly
true.
That would have been better.
I should have acted out a recursive hash table. Man, have you all implemented the like double hashing as your collision avoidance algorithm, where you get to use key value storage recursively? It's sublime. It only works with type theory. So, okay. This is how you do a cargo feature. Do I have actually time to do this? Oh, I'm just going to have to talk because we're getting close to the end of class, huh? Well, what else are we doing today? Is anyone busy today, or can we just go over by like 45 minutes?
I don't know if that's happening.
The way
Wait,
you
I already
do it,
did
you
this?
Just find somebody else that's done it, copy their code and change it for what you want.
I do think that's true, right? So anyway, this is how you use cargo features. And yeah, you just put recursive page table in here as well. Okay. So, what does forthwith mean?
From now on. Like,
Okay. Yeah.
With like fourth going forward.
You
with-
wrote it. You tell us.
I clearly was in an altered mental state when I wrote this. No one says forthwith. Okay. Hold on. What part of speech is forthwith?
Adverb.
Yeah,
Adverb?
I think that's right.
What verb is it modifying?
Um,
Maps?
immediately without delay, especially in official use.
The bootloader immediately, without delay, maps the complete physical map. All right, you got me. I've been bamboozled. Okay, so we have some map. There's some data structure that contains this. We don't really care about the data structure as far as I can tell, but we can print it out. Here, we'll do this. Circ main. Wow, look at all this code. That's crazy. Wow, I don't care about any of these things. Oh, I need that still. Okay. Wait, no, I don't need the unsafe no mangle. Okay. Does that look right? Boot info, end static. Jimmy will teach you about lifetimes on Friday if you haven't learned already. Have you done lifetimes? Just only do static. Or don't.
When you're doing operating stuff,
Yeah.
half the time that is the answer.
There's like no reason to. You probably shouldn't do that in software. But okay, so I'm gonna print out the boot info so we can see what it looks like. Is this gonna work? Really? I have to say this? Oh, it can't have a return statement in it. That's why there was a. Okay. So here's the boot info. Don't overthink this. I think probably you're in the stage in your computing science careers where you're not going to overthink things, right? This is, it's JSON, right? Oh, they definitely are using Certa under the hood here somewhere, right?
That's just a display for a struct.
Yeah.
That's a debug implementation of a printing of a struct. It's a struct as memory map, which is an array of memory regions.
Wait, I was trying to click it and I actually can't. How do you really, is it like Control-Alt and then you get your, yeah, there it is.
All GA.
Okay. Yeah, I can't mouse over it. That's fine.
Yeah, you can see it's even telling you what to do. Press Control and G to release grab.
In fairness to me, I thought I had pressed that, and it turns out I just didn't hit the G. Okay, so you have a memory map, and then you have one other thing in here. You have a physical memory offset at the end. So what's that? That's the number we add to get our linear transform. So we can extract that. No, there's other stuff in here. Do we care about any of that? Probably not. And then what do? I don't press this button because I think that doesn't work for some reason. We click in, Control-Alt-2, quit, boom. That's the boot info. What time's this class end? It's like 10 minutes, right? I've completely lost my mind.
It's like 1 minute.
Oh, it's in 1 minute?
It's in 5 seconds.
Oh, is it? Okay, it's 2:40?
Yeah.
Okay. Yeah, this is pretty much your homework, so that's actually an okay place to go. I think I'll just leave the slides as is, and you can go through them referencing while you're working on the homework. I don't think I'll, like, move stuff around. Yeah. Have fun. Are you meeting on Friday? Because it's a weird week. Just update everyone in Discord. Yeah.
Probably. I don't know.